Okay, so this is a big day, a big lesson, because we're now going to shift gears from just thinking about integrals of regions in space, and now we're going to add vector fields into the mix. And so we define a vector field to be a function that's assigning a vector to each point of the domain. And I'd like to actually start with a video that I really enjoyed normally showing in class that helps explain and visualize vector fields first, and then we'll come back and try a couple of examples.
Let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be three-dimensional, or even higher, we're just going to be looking at 2 dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon. What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And what can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow?
Okay, so we're going to come back to some of those questions that he asked in the video in the coming lessons, but right now we're just going to practice with how we can visualize vector fields. And in the video, he said we were only going to stick to 2-dimensional vector fields. In this class, we will also be looking at 3-dimensional ones. But right now to practice, let's just practice sketching a 2-dimensional vector field. So I'm going to lead you through how to do example 1A, and then I'm going to have you put it on pause and see if you could sketch for me what 1B looks like. In general, with a vector field, you're going to take points. And so let's evaluate F, let's say at 1, 0. I'm just going to pick some random points. And typically, I like to do them on the axes first. So I'm going to make a list of points on the axes. And I'm just picking 2 random points on each of the axes. And you're just going to plug in. So let's start with this first one, f of 1, 0. I'm just going to plug in 1 for x, 0 for y. And so this is going to give me the vector 1i plus 0j. And now I'm going to go sketch that. I'm going to start at the point 1, 0. And I'm going to sketch this vector that's just 1i. And then same thing you'll notice with f of 3, 0. I'm just getting 3i. So I'm going to go to the point 3, 0 and sketch this vector that's over 3 in the x direction. And I can do the same thing for all the other points that I picked. And I can see, at least along the axes, that these are pointing radially outward and they're getting longer the further we go out. It's also helpful to pick just a few points in each quadrant. So I could do, like, let's do f of 1, 1. So we're just going to try to get a visual as to what this vector field's doing. That's just going to be 1i plus 1j. So I'm going to come over to the point 1, 1 and draw a vector that goes over 1, up 1. And you can imagine if I did that here, I'd get one that's going like this, and here is what this. And then if I went a little bit further out, like we could do f of 3, 3, I'm going to be getting, starting at 3, 3, I'm going to be getting a vector that's, well, it should look like it's going over 3f3. Hopefully like that. Like that. And so you can see this vector field is pointing radially outward at any point, and the vectors are getting longer the further we go out. So go ahead and try to put this on or put it on pause, and I want you to see if you can sketch for me what this vector field in 1B will look like. Okay, and so if you've done this, I just filled in a few of the vectors here, but you can see we're going to get this clockwise rotation in this vector field. And while I was doing this, I realized I had a typo earlier over here. This I had accidentally listed as f of 3, 0 again. I meant to be f of 0, 3. So we fixed that here. Oh, and these over here are all just supposed to be e's, not f's. Okay. But in general, you get the idea. And we could also go look at this. I like to also look in a graphing software. So let's look at GeoGebra. And here's that vector field in GeoGebra. So again, we only did a few of the vectors at given points, but you could get the same idea that we see here when you use graphing software. All right,